First of all, I would like to thank the organizers for the kind invitation to take part on this meeting. And also, I'd like to thank all of you online attending the meeting and attending my talk. Okay, today I'm going to talk about what is the impact of surface coating magnetic nanoparticles with coating increasing the thickness. So next slide, please. Okay, so here is my agenda for today. Briefly, I will comment about cobalt ferrite nano platform. And then I will summarize how the chemical synthesis is performed to produce cobalt ferrite nanoparticles, and in a first step, and then in a second step, how we manage to surface coating the cobalt ferrite nanoparticles with a set of amino acids. And then I will present the main characterizations, structural and morphological characterization of the samples, not only the native cobalt ferrite nanoparticles, but also the surface coating cobalt ferrite nanoparticles. And then I will skip to presenting you the magnetic properties and the model picture to explain. I will emphasize in this point how the surface thickness influences the magnetic properties. And then I will summarize my talk with some key points. So next slide, please. Let's start. Okay, thank you. So here is, you can see on the upper part some important points regarding the cobalt ferrite nanoparticles. So this material has a very high coercive field value, large magnetic moment, and then surprisingly, it is a very much biocompatible material. And that leads to important applications in the biomedical field, like, for instance, the use for magnetic hyperthermia, and all use for designing drug delivery system, and also to fabricate contrast agent for magnetic resonance imaging. On red, I emphasized the biomedical applications. However, due to the high coercive field value and large magnetic moment, this material can be used in spintronics, recording media, and also to fabricate permanent magnets. On the lower part of my slide, to emphasize on the biocompatibility of cobalt ferrite nanoparticles, I'm showing you two slides, morphological slides, biomorphological slides, where we use to inject in mice and then to analyze the impact of this nanomaterial in the mouse liver. On the left-hand side, you can see on the black arrow a inclusion of cobalt ferrite nanoparticles coated with citrate, and the nanoparticles are observed inside the Kupffer cells in the liver, and there is no sign at all of any side effect. No liver toxicity was observed. On the right-hand side, it's a different formulation. You can see also the black arrow. The cobalt ferrite nanoparticle was injected in the animal using a magnetoliposome, actually. So in the magnetoliposome is surface coated with polyethylene glycol with PEG. And we spot the magnetoliposome inside the capillary. Likewise, in both experiments, no toxicity or cytotoxicity was observed. So that means that the biocompatibility of cobalt ferrite nanoparticles using different coatings actually is very, very much interesting. And that allows us to use this nanomaterial for many biomedical applications, like I mentioned before. Next slide, please. So briefly, here is the synthesis, standard synthesis of cobalt ferrite nanoparticles. Actually, this process can be used to synthesize many different cubic ferrites nanoparticles. So it's the chemical co-precipitation in alkaline medium. And you can see in number one, we started with a aqueous solution of iron and a transition metal like cobalt or copper or iron too. So, and then the synthesis starts with a precipitation in alkaline. You can add different bases like sodium hydroxide, potassium hydroxide, ammonia hydroxide. So this is the first step. The temperature is around 100 C. And then very quickly you precipitate the cubic ferrite nanoparticles. In this particular case, the cobalt ferrite nanoparticles. So the pH after the step number one is very high. You can lower the pH in step two. In step one, the particles are formed with a very high negative surface density, charge density. And in step two, we add some acid, for instance, nitric acid, and then we cross from negative to positive surface charge density. So you may manipulate the system going through the point zero charge if you go horizontally, or from the positive surface charge nanoparticles in order to stabilize the as precipitated nanoparticles, you have to perform a hydrothermal treatment. So the hydrothermal treatment you can see is performed using iron nitrite, iron 3 nitrite, boiling at around 100 C. And what happens in this process is actually you end up with a sort of core shell nanoparticle. The core is the cubic ferrite, in this particular case, cobalt ferrite, and a very thin shell layer of megamite, actually. So the megamite is the surface layer that stabilizes the system. So you may produce very stable colloids using this surface treatment of the as precipitated cubic ferrite nanoparticles. In principle, this approach can be used for a large variety of cubic ferrites. So this is the first step. Next slide, please. Step number 2 is the surface functionalization using different molecules. In this case, we used a set of amino acids, and the smallest one was glycine. So you can see on the lower part of my slide, the cobalt ferrite nanoparticles plus glycine, and then you perform the surface coating of the native cobalt ferrite nanoparticles. However, there is a very important point in this process, which is the regulation of the pH under which you perform the surface coating. So for every surface coating, you better explore what would be the best pH value to achieve the highest surface grafting on top of the nanoparticle. So we follow this looking at the absorbance of the end material. And then we can, in this case, because we are coating with a molecule that has the carboxyl group, we can look at the carboxyl group absorbance. And as you can see, as you move from pH 2 to pH 5 and pH 8, you can see that the intensity, the relative intensity of the carboxyl group increases as a function of the surface coating pH. So you choose the best pH value for any kind of surface coating to optimize the surface grafting on top of the nanoparticle. Next slide, please. Okay, so here is the set of 5 different amino acids we use to coat. The smallest one, which has 2 carbon in the structure, is glycine. The next one with 3 carbons is alanine. And with 4 carbons, we have the aminobutanoic acid with 4 carbons. And with 6 carbons, we have aminohexanoic acid. And finally, with 12 carbons, we have the aminododecanoic acid. So this way, we can manipulate the surface coating thickness. And the surface coating thickness, actually, it modulates the magnetic properties of the end material. Basically, it does because the interaction between particle and particle. So the particle-particle interaction is modulated by the thickness of the surface coating. And that influences the magnetic property of the end material. Next slide, please. Okay, so here is a typical crystal structure of the synthesized nanomaterial. You can see the standard reflection line from the X-ray diffraction data, typical of cobalt ferrite. So you can see the ICDD card number, the peaks appearing on the spectrum. It agrees completely with the ICDD data card. And moreover, we observe the same spectrum for all surface coating materials. This one I'm displaying on the screen is for the native cobalt ferrite nanoparticles, but all the recorded X-ray diffraction data for the set of 6 samples. The first one is the native, and we have extra 5 more samples with 5 different coatings. All of them presented the same X-ray diffraction data. So next slide, please. Thanks. As for the morphological aspects, I'm showing you the transmission electron microscopy and also the high resolution transmission electron microscopy. So from the TEM data, from the TEM micrograph, we can extract the particle size distribution. You can see on the right-hand side, the particle size distribution. The vertical columns are the experimental data. And the data, the particle size distribution was curve fitting. Using the log normal distribution, you can see the expression of the log normal distribution. And then you can extract the mean size, which is about 6.7 nanometer, and the size dispersity, about 0.42. So in the lower part of my slide, I show a table that collects the extracted morphological data, not only for the native, which is the first row. I stand that as cobalt ferrite at core, so that's the core for a one set of synthesis. For this particular set of synthesis, we found the mean size of 503 nanometers and size dispersity 0.32, which is a more narrow particle size distribution as compared to the one I showed the particle size distribution in the upper part of my slide. So the table that I show in the slide refers to a different synthesis from the one I'm showing on the upper part. So, and then if you look at glycine coated cobalt ferrite nanoparticles, the mean size is about the same. Size dispersity is about the same. And likewise, if you look at that aminobutanoic acid coating, it's the same mean size and roughly the same size dispersity. And finally, with the thickest coating, which is the aminododecanoic acid, the mean size is about 5 nanometers, and the size dispersity is pretty much within the range of the rest ones, so within the error. So typical size of this synthesis is between 5 and 7 nanometer in mean size, and the size dispersity is about 0.32, which is very nice quality samples actually, as far as the size dispersity is concerned. Next slide, please. Now let me show you typical magnetic data. So in both slides, I show you the hysteresis curves recorded at about 400K. And you can see it is the material in this temperature is in the super paramagnetic state, and the data magnetization versus applied field shows typical behavior of a super paramagnetic material. And we can perform the curve fitting of both data. On the left-hand side is just the native cobalt ferrite nanoparticles. On the right-hand side is one example of surface coating with glycine. Remember, glycine is the shortest amino acid chain, carbon chain length. It's the shortest one. And we can perform the curve fitting of the data using the expression I'm showing on the lower part of my slide. On the right-hand side, the first term refers to the paramagnetic component or diamagnetic component, actually. And the second term refers to the standard superparamagnetism behavior, where L refers to the Langevin function, actually, and F stands for the log normal distribution function. Of course, from this fitting, you can extract from fitting the 400K magnetization data, you can extract the mean size and the size dispersity, which is included in the legend of both insets on the left and right-hand side plots. And then you can see that the data extracted from the morphological data extracted from magnetization data is exactly the same as we extracted from the transmission and electron microscopy data. So next slide, please. Here again, two more samples at magnetization recorded at 400K. So we have the aminobutanoic acid coating of the cobalt ferrite on the left-hand side. On the right-hand side is the aminododecanoic acid, which is the longest carbon chain in the surface coating. And again, the fitting, you can see how good the fitting is using the same model. And the mean size and size dispersity extracted from the curve fitting. Besides extracting the morphological data from fitting, the magnetization data, we can extract also the saturation magnetization of the particle itself. So in the lower part, you can see the saturation magnetization of the particle in terms of EMU per volume. And then you can see the values for as you perform the surface coating. The first row is the native. And as you perform the coating, you can see this saturation magnetization per particle changing. And that change is related to the particle-particle interaction I'm going to discuss in the next slide, please. Okay, so here is a saturation magnetization as a function of temperature, actually. So you can see the symbols are experimental data, and solid lines are the best curve fitting using the block type law on the right-hand side. So from this fitting, we can extract the saturation, normalized saturation magnetization of the sample. And then we can fit this and extract the B term, prefactor B, and also the exponent beta. And the table in the lower part collects those data. So you can see the saturation magnetization of the sample at 0K, which is the first column of data. It has the maximum for the native cobalt ferrite nanoparticle. And as you increase the thickness of the coating layer, you see a systematic reduction of the saturation magnetization at 0K. So also we collect the prefactor B and the exponent beta. So it's very important to emphasize that the exponent beta is about the same for all samples. It is the same within the standard deviation of the parameter. But here, the key point is the systematic reduction of the saturation, the 0K saturation magnetization of the sample. So as you increase the thickness of the coating layer, meaning the number of carbons in the coating molecule. So you reduce the saturation magnetization. So in other words, you can modulate the saturation magnetization by changing the thickness of the surface coating. And you can see that the difference between the native, which is 77.2 EMU per gram, is quite different from the saturation magnetization of the thickest surface coating, which is the last row aminododecanoic acid. It goes down to 55.2. Let's say it's a very important variation between the native and the surface coating with the thickest layer, with the thicker layer. So this is a way to modulate the saturation magnetization, and of course modulates all the applications. For instance, the magnetic hyperthermia of the end samples. Remember, all of them are biological friendly, and then they can be used for biomedical applications. Next slide, please. So here is a very brief description of the model picture to explain the change on the magnetic properties, which is based on particle-particle interaction. If you look at particle-particle interaction, there are two main components for particle-particle interaction. The first one is the exchange interaction between neighboring particles. But that is a typical short-range interaction. And the influence, of course, is independent of the coating. Because after you coat your nanoparticle, the exchange interaction just is ruled out completely, because it requires the surface of the nanoparticles to be very, very close together. So as you make your first coating, regardless of the thickness of this coating, the exchange interaction, it doesn't contribute for the end magnetic properties. But the second mechanism for particle-particle interaction, which is the dipole-dipole interaction, is a long range. And that depends on the coating thickness. And that is the explanation for the systematic reduction of the saturation magnetization at 0K as you increase across the 5 different coating we performed. So as you increase the thickness of the coating, the dipole-dipole interaction reduces, and that reduces the saturation magnetization at 0K. Next slide, please. So I will then summarize important points regarding my talk today. First was the very successful synthesis of core shell cobalt ferrite nanoparticles. Remember, the core is the cobalt ferrite and the shell is maghemite. So we have a thin layer of maghemite on the surface in such a way that the core is preserved on its phase and on its magnetic properties. Second point is that the shell thickness, it indeed modulates the physical properties, and in particular magnetic properties of this collection of nanoparticles. And it modulates in a very systematic way, which is a very important point. The third aspect is that the hysteresis curves of all the samples I present to you today, they exhibit super paramagnetism only at 400K. we, of course, observe the magnetism of this collection of samples at lower temperatures. As I showed you, the saturation magnetization plot, which has the saturation magnetization versus temperature. So, however, at 400K, all the samples present super paramagnetism, which is very important for some applications, and applications that take place at temperatures near to 400K, like, for instance, the magnetic hyperthermia. So the fourth point is the saturation, actually, the magnetization does not saturate below 100K. I didn't show you the data, but this is what we found. Even if we push the applied field up to 30 kilohertz, so we have no saturation magnetization below 100K. This is because of the magnetization of the surface thickness, of megamite surface thickness, very likely. And finally, the strong particle-particle interaction. We found a very strong particle-particle interaction, not only at room temperature of 400K, but also in the whole range of temperatures we investigated the sample. So we investigate the sample from 5K up to 400K. So particle-particle interaction, it takes a very important, plays a very important role in defining the magnetic properties of this material, of collection of materials. Next slide, please. So finally, I want, again, thanks the organizers of this meeting for a kind invitation to be here today and join you all. And also, I would like to thanks all of you online attending my talk. And you can see, I'm sorry, you can see in the lower part of my slide my contact. Please, if you have any question, I'll be happy to take it. Thank you.
Hello.
Yes.
Hello, Dr. Paul. Hello, Dr. Paulo.
Yes.
I have one question. This super magnetization you achieve, paramagnetization you achieve due to the amino acid coating or anything else?
I'm sorry. There is a lot of noise in the background. Would you please summarize your question in the chat? Then I can
Okay.
pick up the question and answer it to you, please.